All right, guys, we are here for the very last lab of the remote sensing part of our course. And in this last lab, as I promised you, I'm highlighting the different methods we can use in order to extract information from our data. And this is for what you have due for the final assignments. So I mean, in this lab, so I'm using some data in order to show you how we can, which procedures we can use in order to extract this kind of information. All right. In my case, I decided to use Sentinel-2 data because we know everything concerning Landsat data, especially Landsat 8. And so, I mean, I'm using this kind of data in order to give you all the different possibilities. Of course, what I'm going to show you, it's applicable in the same and exact way for the Landsat data. All right. Let's start with these labs and taking into account that I'm using Landsat, I'm sorry, Sentinel-2 data, I need to load that not as metadata because unfortunately this version of Envy is not opening the metadata in the last format has downloaded by the SHE hub of the European Commission, as I showed you in the open access in the open source data access video. That is the last video I recorded for you. So I'm going to open this data, and I have this data in this directory here. You see, this is the data I've downloaded. You see, this is downloaded uh, just taking into account the name from the Sentinel-2A platform. The sensor is MSI, and the processing of the data is the 2A processing. So that means that are processed bottom of the atmosphere. And the acquisition date you see from here, from the first part of this alphanumeric name, is the 23rd of August 2020. So I decided to download a summer acquisition in order to have the possibility to extract the different vegetation asset that I have in my area. So I'm going to here, and you remember from here, this is a very long name as downloaded by the Sentinel portal. And you see, I need to go here and then to this folder that is called Granule. All right. In this folder, we have also this other subfolder. Going here, you see, I'm going to the image data folder, and finally in this image data folder, I have the three different subfolder. The data at 10 meters of geometric resolution on the ground, the data at 20 meters of geometric resolution on the ground, and the 60-meter one. For this as final assignment, my suggestion is try to use the 10 meters, the best resolution, geometric resolution as possible, as I mentioned you during the live lecture. And if we will not able to use everything, we can use the 20-meter geometric resolution. So I mean, I can just open the 10-meter resolution, and from here you see I'm selecting, just keeping press the control button on the keyboards, the B2, I'm sorry, the B2 here, the B3 and the B4. Uh, Here you can find also the HDR because I already opened this file before, but you will find only these files here. So B2, B3, B4, and B8 with the extension JP2, that is a JPEG extension. So these four bands for the 10-meter resolution. So I'm going to open these four different files, you see. And just to have you some information concerning this image that I selected, so you will select whatever you want. In this case, just to change, I selected this area here. So you see this area is, let's see where we are, views. So let's go to the reference map link here. And you see we are in Rome, okay? And this rounded feature here is what in Rome is called grande raccordo anulare. That is a sort of highway that is surrounding the city of Roma in order, and is collecting, you see here, all the other roads coming from all the other direction. All right? Consider that here, in this point here, he's from Rome, we have the Fiumicino Airport, that is the main international airport in Italy. All right? So we are here, and so you remember what we will do. I already showed these things in the open source access data lab. And so in order to process all this data, unfortunately, the data, of course, you can see here in the lower left part of the layout, you see it's a georeferenced, but unfortunately, if you don't go to every single band and right-clicking, go into the view metadata, edit the metadata, and then simply pressing OK, and you see that this band is moving up of the list. If you are not doing that, you will not be able to layer stacking all the data, so to encompass all the data in a single file. Because the first things we need to do is just to have all these four bands in the same data. So I already did these things, and so I'm opening the file that is representing this data. So I'm going in my folder. You see, I have a data, a folder that is called Rome, and I'm opening this file that I have created with the layer stacking option. Do you remember? Is in the toolbox in the raster management. I will show you that. So I'm opening this 10 meters dot dot, and I put this file here. All right. And just to remind you that in order to perform the layer stacking, you need to go to the toolbox here, and just in the raster management folder, you will find everything here. So let me take this one and double clicking on layer stacking, and you remember you can import all the four different bands here. If you need, if you need, you can reorder the files, and then you can save the whole data. Right? I'm not doing that anymore because I already explained to you all how you can perform this operation. All right. So this is the 10 meters data. So I can take these single bands, and I can remove all the four different bands that I used at the beginning, because otherwise, I will have some fuss here, because I don't want to have all this data. So if I'm going to the data manager, you see in the data manager, end of the bottom of the list, I have all this data. I can also take this data out from the data manager. All right, maybe it's better. All right, the first four bands, and so I have only this one. So for example, in this case, I can just, for example, add uh, uh, the fourth color image, B8, B4, and B3, all right? And I can load the data, you see? And we are sure that this is Rome, where all the build-up area is in cyan, and all the vegetation, of course, is in red. You see that also here, you see that in brackets, at the end of these things, I had also the wavelengths, because the wavelengths, you remember, I'm closing the raster management here in the toolbox, are necessary in order to use the spectral indexes. If you have not added I'm sorry, the wavelengths number, in this case in nanometer, you cannot use the spectral indexes. So you remember how we can add this data? I mean, in order to add the wavelengths information, right-click the results of the layer stacking, go to the view metadata, edit the metadata, and then here you need, you see, I already have all these things here, you see. This is the sensor type. I had Sentinel-2, and I had the 4 different, you see, wavelengths with the wavelength units, that is nanometers. How I can add these things here? Now I cannot do that anymore. But I mean, you will see here in this plus green symbol here, adding, you can add these things here, and you will see that is not anymore here, because I mean, I already used that. You will find wavelengths. So click OK, you will add the wavelengths. You can put sensor type Sentinel-2 if you are using, of course, Sentinel-2. You should put that here nanometers, and then one by one you have to add the central wavelengths. Where you can find the central wavelengths, you can find the central wavelengths here, for example. You see, in the you remember in the ESA official site of the Sentinels Copernicus.eu, you can check in the multispectral instrument, the MSI, all the different wavelengths. And you see here, this is for the Sentinel-2 A and B, because they are different. And here you have all the different geometric resolution of the different bands. All right? So in this case, I have everything here. And so I did the same things for the 20 meters data. And so I can open also these data sets you see in ROM, and I have already created the 20 meter 20m dot layer stacked data. So I'm opening that. All right, you see here is I already edit the metadata. I add already the wavelengths, the central wavelengths in nanometers for Sentinel-2 uh, sensor, and you see that by default here I have the visible. So if I'm going to the data manager, you see that I have the 10 meter data and the 20 meter data. So let's enlarge these windows, and you see I have all the different wavelengths here. So you see that the 10 meter data band is composed by band 2, 3, 4, and 8, that are the blue, green, red, and near infrared, while the 20 meter data, you see we have these this blue band here, the same blue, red, green, and red. Then we have other bands here, 5, 6, and 7, that are in the red edge of the visible. The 8A here you see is more or less the near infrared, and then 11 and 12 are the mid infrared in microns, that is 1.6 at 2.2. Right? So we have everything here, and for example, also here in this band selection, we can compose as first color the band 8A, and then we can add the 4 and the 3, and that will be 8A, 4, and 3. That will be the first color image. You see here at 20 meter resolution. So you see, I'm opening all these different association here, and we have, you see, the 10 meter one is the visible bottom of the list. Then I have the 10-meter false color, the 20-meter color, true color, and the 20-meter false color. All right. So this is the input data, multispectral data in my case. And now we will start with the different methods in which we can extract the information we need. In this case, now we are starting with the processing of the data. In order to start with this kind of processing, according to me, the best things to do in this case is not to have all the different layers stacked in the same views, but maybe just dividing at least in two different views. So encompassing in one views the data at 10 meters on the ground, and in the other view the data that are regarding the 20-meter on the ground. So in this case, what we can do, we can go to the 20 in the layer manager in the 20-meter data, the two visualization, and just remove this couple of visualization at 20 meters. I remind to you that removing that from the layer manager doesn't mean to remove that from here, from the data manager. In the data manager, you see the data are still there. So, for example, if we are going to the 20 meters data, I am going to enlarge these windows, otherwise I cannot see all the different brackets with the wavelengths. I mean, again, I'm taking here and by associating to the RGB channels, the bands 8A, 4, and 3, and I put that, just checking here in this box here, I'm loading that in a new view, and I'm loading this data, all right? So in a new view, you see, I have that in another view. And of course, I can also add, for example, a visible here. So just associating to the RGB 432 and loaded that in the same view. You see, we have the cyan frame. So that means that this is the view that is selected. So whatever I'm uploading that in this kind of view. So I'm loading also the visible here, and now I can close the data manager. So you see now I have the visible and the near infrared. So one thing that we can do is, for example, just go to the top of the list of the second view, this data here, that is the visible, right click that, and just you see here, never done before, because we did that with the drag and drop mouse. We can send, for example, to back this view. So if we are sending to back this view, you see, I mean, we have all the 20 meters back here, all right? And here we have the 10 meters, all right? So, I mean, you can also walk with this kind of data. So let's say that now you remember, in order to move in the same wave in the two views, of course, we can go to the main menu views and we can link the two views. All right. So we are linking all and we are pressing OK. All right. So I mean, let's start with just downloading the data. I'm sorry, reducing the zoom of the image in order just to check what are the characteristics of the two data. So in this case, I mean, these are the visible. This view is 10 meters and this one is 20 meters. You see that is quite easy to understand if I'm zooming in the difference of these two data. You see, this is the, let's set a particular zoom factor. This is 10 meters, this is 20, of course. And so, for example, you see this is the Stazione Termini, that is the railway station in Rome. You see here, and for example, you see here that we have here the Colosseum. You see here, this is the Colosseum, and this is the Fori Imperiali part, all right? So it's quite easy to see the different features at 10 meters. It's tricky. I'm sorry, this is the railway station. This one, the Termini, is this one. And this is the Colosseo. All right, it's quite easy to check the different features here in the 10 meters. Here is a little bit complicated just because of the different resolution of the data. All right, so what we need to do right now, we need to remind which is the final goal of this assignment. And the final goal of this assignment, as we can see here in these things here, is just, you see, just to extract from the remotely sensed data, and these are satellite multispectral data set, we should process this data in order to extract a simplified land cover map, including, depending of course on the selected area, the following classes. You see? So if we are going through these following classes, for example, in the image we are analyzing right now, of course, the built-up areas are present, like the permanent water bodies, because we have the river Tevere, that is very famous also because it's very famous from the Latin word. Of course, here we don't have any snow and ice, so I mean the third class is not present here, and not only for the month we are taking into account, because this image is acquired in late August, but because in Rome it's very rare to have snow there. Then here you see we have cropland, forest, bare soil or sparse vegetation, and then herbaceous vegetation or and shrubland. In this case, all these things are on the image. There are, of course, cropland that could be mixed with this herbaceous vegetation, because I mean, it's very, it's not. I don't think that there are any cropland in Rome. While there will be some cropland outside of Rome, while in Rome we will have something. For example, urban parks. There are of this kind, so herbaceous vegetation and part of forest. There are forests in Rome. That means there are parks with very dense and tall trees, and we can check these things here, and also these bare soils and sparse vegetation. So this is the classes we need to extract. And so in order to extract these classes, I'm going back to this thing, to our image. I mean, the best things is, for example, considering that you see this is only a very small part of the image, because I mean, the whole image is this one, you see, in my case. And if you are using Sentinel, it's quite similar to have this kind of scene. So I have all this water. We have also here a very large lake that is north of Rome, for example. And here I have also other interesting part. For example, here in this part here, as I mentioned before, this is the Fiumicino International Airport, you see, that is in the middle of these crops. So, for example, my suggestion is just to try to classify all these scene, and then once classified and one extracted, classified in general terms from the philosophical terms of view. That means that when we have extracted all these classes, of course, snow and ice is not there. So, I mean, we are not taking care of these kind of classes. But when we have extracted these 6 possible classes out of this image, we will define a small subset that is, encompassing only the city of Rome. For example, just taking into consideration the Grande Raccordo Anulare, so the highway that is surrounding Rome as more or less a border of the scene. But my suggestion is let's try to use everything, and then just to subset the final data. How we can proceed in this way? Of course, we pass through different possible methodologies. These different possible methodologies are regarding the possibility to use one single band. So, for example, using density slicing, for example. You remember we can also use a couple of bands using scatter plots in order to isolate particular land covers. Or we can use, for example, other methodologies, like for example, here you see spectral indexes or band math. For example, extracting surfaces that are homogeneous using spectral indexes or band math. We can also use filtering, but I mean filtering is something very particular, but definitely we can also use classification algorithm, all right? So I mean, we can approach the different possibilities just to have a simple test. But before starting from that, my suggestion is that for these 6 different classes that we are searching for in this data set, that means built up permanent water bodies, cropland, forest, bare soil or sparse vegetation, and herbaceous vegetation and shrubland, no snow and ice. I mean, the best things to do is just to extract a region of interest for every one of these single 6 possible classes. Because if we are extracting since the beginning region of interest of these classes, we can, of course, be more precise on the statistical distribution of this data, and also take into account, for example, also not only the the statistical distribution, but also, for example, the spectral signature, in order to understand if one single band could be enough in order to extract this particular layer, or we need more bands. Because I remind to you, in 10 meters, we have 4 different bands, 3 in the visible and 1 in the near infrared, while in the 20 meters, we have 9 different bands. So I mean, the multispectral density of the 20 meters is bigger than the 10 meters. So we need to check also if we can use, of course, we prefer to use 10 meters, but the question is that, I mean, only 4 spectral bands are enough in order to extract these classes, or we need more bands? Because if we need more bands, that means that the geometric resolution of the output will be 20 meters instead of 10. All right? So, I mean, from this point of view, we can start with the extraction of region of interest. All right? And so, in order to extract a region of interest, my suggestion is just to work with the 10-meter data set, that is this one, you see, cyan frame. And we can start with this one. And starting with this one, I prefer to use, for example, just not visualizing the visible, the force color. All right? And so, for example, you see, this is Rome, you see? And so what I need to do, I need, for example, in this case, just to extract a region of interest out of this image, all right? Again, here, left side, we have 10 meters, and you see here, we have 20 meters. But the region of interest, I'm going to extract from this data. So I'm working in these views, okay? Cyan frame, all right? So in order to extract a region of interest, I'm going here to this part here, region of interest, all right? And so I'm starting with the first region of interest. This first region of interest could be, for example, just clicking here, row name. You see, I can start with the second one, for example, permanent water bodies. So I'm calling that permanent water bodies. All right? That will be my first region of interest. And of course, in this case, I'm taking that in blue. All right? So here, for example, you see I am in the middle of Rome. This is the Tevere River. This is a river that is passing through Rome. So I'm zooming here, and I'm not selecting the original polygon, but I'm taking out the polyline tool, because now, starting from this bridge here, you see, stay in the middle of the river. I'm clicking here in order to extract the water of the river that is in the middle of Rome. When finished, right click with the mouse and complete and accept polygon. All right, this is the first one. So I can also use a other part of the image. For example, I'm going here. You see, I can add another polygon here. Just click in this case, stay away from the border, and then close the polygon. In this case, the polyline. All right. So I take out three of these lines in Rome. For example, now I'm moving here uh, to the northern part of the image here. Okay. Maybe here, just close to the stadium. For example, in the middle of these 2 points. So I'm going here again. You see now the mouse is changing the properties, just staying in the middle here. All right, from bridge to bridge, I'm closing that. Of course, don't encompass any bridge here. All right, this is the permanent water bodies. But I mean, this is the only water that I have in Rome. Yes, this is the only one. Apart from this one, for example, let's check if this is not water. This is a very dark area, but this is not water. So in Rome, we have only this kind of water, but we have something more here. For example, we have this big lake, north part of Rome. Why don't we can take also this water? So in the permanent water bodies, now I pass to the polygon, okay, and I'm extracting this very huge area here, all right? And I complete and accept the polygons. But I have also the sea here. So maybe I can just go in front of the international airport and just to take a very large area of water here, okay? And so these are the different polygons that are composing my different rows that are called permanent water bodies. So in order to check these things here, I can just and we have saved that, and we need to save that. So I'm going to the ROI tool window. I'm going to File, and I'm save these things here. So you see permanent water bodies. I'm selecting the position. So I have a folder that is called ROM. So in this case, I call that ROI, and I put that 10 meter, because I mean, I saved that in 10 meter resolution. All right. So I'm going to open that. That will be the extension. We'll have the extension XML. So in my new folder ROM, I have the ROI extracted on the 10 meters resolution. All right. So I can press OK. So I save that. And now, for example, from these permanent water bodies, I can go here in the compute statistics symbol, and just pressing that, I mean, it's calculating the statistics of that things here. And you see, this is the spectral signature of the data. So you see here we have with the black line the average, the mean value, because we have 4 different bands. Here on the x-axis we have the wavelengths in nanometers, and here the data value. And so you see here this is in black the mean value. So I mean is reflecting in the blue very the reflection is very low. I mean, because most of the energy is absorbed by the water. But you see that increasing the wavelength, the absorption is increasing, of course. You see, this is the green line are the standard deviation, and you see that the standard deviation is very low here, because consider that the variation of this data is more than 65,000 in digital number. So I mean, you see, it's very low, while the max and minimum value is very big. That depends on the case that, for example, I have the doubt that in the OpenSea I also encompass some boats, for example, that they reflect very much in comparison with the water. But I mean, these are outliers. I mean, one single cell is enough in order to have this particular value. What is really important is to have a very low standard deviation, right? So these are the data. And so, for example, if I'm closing these things here, I save that, and I'm passing in the 20 meters frame. You see that now it's the cyan frame is on the right view, and you see that is highlighted the 20 meters. I can reopen from here the region of interest tool, and I can, for example, open the previous data. So I'm taking these things here, I'm opening that, and you see in the data manager, I'm just expressing where I want to associate these things here. I'm associating to the 20 meter, but you see, it's not possible because I mean, it's the only possibility is to associate that to the 10 meters. You see that for 20 meter, the load data is not available. So if I'm taking that for the 10 meters, or in this case, for these things here, I can load this data, all right? So I'm choosing the layer, and I'm choosing the 20 meter dot, all right? That is, this is the visible, and this one, I'm sorry, this is the visible, and this is the false infrared, the 20 meter, and I put in that here, all right? And you see that I have also that in the 20 meter, all right? So I'm closing the data manager. You see that I have both the region of interest in both the two visualization, all right? So consider that now we have these two things here. I can close the region of interest tool. You see that the ROI are on both the images, because the ROI, when we draw these polygons or these polylines, we are drawing that in cartographic coordinates. So of course, they are also overlapping over this file here at 20 meter. And so, for example, if we are going to the permanent water bodies at 10 meters, you see cyan frame, just right-clicking with the mouse, I can have the statistics started from here, all right? So it's computing the statistics like before. This is the 10 meters, all right? I'm trying to close that because it's too big, all right? So this is the 10 meter, all right, with the spectral signature. I want to have that a little bit smaller, and I can do the same things with the 20 meter. All right, so from the 20 meters, right click with the mouse on permanent water bodies and click over statistics. And now it's calculating the statistics extracted from the 20 meters. All right, you see here for the 20 meters, it's different, of course. I'm sorry, I'm trying to close it. All right, is different because here we have more bands. So you see, this is the first part of the image, what we arrive here till to 800. But you see in the other data, we have also the mid-infrared. And so this is the situation in the mid-infrared. All right? So you see, this is the spectral signature of these permanent water bodies. For the 10 meters, 4 bands, and for the 20 meters, 9 different bands. All right? So this is the extraction of the first region of interest. So we are going here again in the first uh, 10 meters resolution data, I'm clicking over region of interest tool, and now we are going to add also the other region of interest. All right, this is the first region of interest we defined. And so we can continue, for example, defining as the presentation, for example, the built-up areas in order to proceed with the definition. All right, so let's go to the 10 meters data sets. All right, we are going to the built-up areas. All right, here it is. And so, for example, in this case, we are defining a new row is, all right, and defining as name, you see, built up areas. All right, let's check that has, I don't know, something like that, maroon, for example. And let's start with defining this area here. I'm defining some building blocks in order to um, to define something that is uh, okay for the registration. So, for example, also here I has some built-up areas. All right, let's zoom out and move. For example, here you see this is the Vatican's. For example, this is the cathedral, and this is the big place that we have. For example, we can also consider the possibility to define the area of the plate or the square here has a sort of build up areas. This is something that is not is artificial. It's fully artificial, this area, so that's okay to consider that as built up areas. Let's go with some other areas. For example, this one is the railway station, the terminal one. All this area is for example, this one is characterized to be a built-up area. This one here. So let's consider also these things here as built up. All right, and let's check if we have something that is big enough in order to be considered. For example, we have also this building here, you see. All right, and I completing and accepting all the polygons. And for example, here you see we can again save everything. So we have permanent water bodies and build-up area. We are saving with the same name, so region at underscore 10 meters, region of interest. They are already there, but I overwriting all this file. And for example, just to see what is happening, I just see the spectral signature of these things here. All right. So this is the second one. Now I'm doing the last one. For example, let's consider in this case the possibility to define what we call forest. You see here from the 10 meters, this is an area of trees. You see here that the texture is typical of trees. So let's define a new area, and this new area here is forest. Let's put that like dark green, this one. All right, and this is forest. You see, I'm completing that like forest. These things here is all, they are all trees, the crown of trees. And I want to just check if there are something similar around the city. Let's check if we have something similar. For example, let's check if this one is forest. All right, should be, but I'm not really sure because it's around the river, so I'm not really sure this is forest. Okay, this is forest, you see, and so I can go here and define this area here, complete a polygon, and then just to be sure, I can go out of the city and just look for some other forest area here, for example. Let's check. You see, these are not really. I'm not sure that this is this is forest. Maybe it's something similar, but not forest. And so let's check if we have something. Okay, here around this lake. Okay, around this lake, you see, I'm pretty sure that it is part of forest. So I'm trying uh, to use these polygons here and trying to avoid these black holes. All right, and this is forest. And so for the next, I'm going to um, to define, apart from built-up permanent water bodies and forest, I'm going to check if there's any cropland or bare soil. So we will see as soon as I finish to define these rows. All right, so we are back here, and I defined five of the different areas. You see here we have the list. So we started with the permanent water bodies, then with the built-up areas, forest, and then herbaceous vegetation and bare soils or sparse vegetation. I didn't define, of course, snow and ice. And I decided to define a class that is encompassing herbaceous vegetation and cropland, having, for example, here in the surrounding of Rome, not this class of cultivation. So, I define all in the herbaceous vegetation, trying to encompass also the urban parks. So we have this data, and we have all these region of interest, and so we can close these things here. We can go to the 20-meter dot, all right, opening again the region of interest uh, uh, windows, and opening the same windows also for the other data set at 20 meters on the ground. I'm loading the data, and I'm using that for the fourth color image. You see 8A, 4, and 3, 20 meters data. This is the, uh, the file I need to load the data. And you see I have also for these 20 meters data set all the region of interest. All right, so I can close everything. And for example, I just can check in the 10 meters if data set, if to see the right clicking on the region of interest of herbaceous vegetation. I'm clicking with the right button of the mouse and taking out the statistics. All right, as before, this is the spectral signature of this kind of vegetation. You see, we have a relative maximum in the green part, an absorption peak in the red band, and then a very fast increasing and a maximum, absolute maximum reflection in the near infrared. This is for the 10 meters. We have only 4 different bands, but we can do the same things for the 20 meters one. I'm going here to the herbaceous vegetation, right-clicking with the mouse, statistics, and here I will have the same spectral signature you see with the 9 different bands. You see the behavior of the spectral signature, maximum in the green, peak of absorption in the red. You see here we have 2 more bands in the red edge. You see that is characterizing the cultivation here, and then a maximum in the near infrared and the decreasing in the mid infrared around 1.5 and 2.2 microns here. You see, so these are for example, the spectral signature for the vegetation, for the herbaceous vegetation. And then, for example, just to check, we can have the same things for the bare soil or the sparse vegetation. So 10 meters, here it is the spectral signature. You see it's increasing. And let's check also in the 20 meters data sets. And this is, you see, this is the first part that is the same here. And you see that in the mid-infrared, the behavior is changing. All right. So, I mean, this is the things here. So let's go ahead with these things here. So, I mean, for example, let's check, for example, and I will try only for one classes at a time for every single methods. So let's start with the density slicing, for example. And in the density slicing, we can, for example, move in order to check the permanent water bodies. Let's check if we can extract that from one single band in the 10 meters resolution data. So let's check first how is the spectral signature and how the statistical data of the ROIs that is characterizing these permanent water bodies. So right click in the 10 meters data sets and let's check the statistics for these things here. All right. The statistics, I mean, the spectral signature is not something that is really interesting me, the graphs, but I'm very interested in the data. So you see here, for example, that for band 4, where I have the maximum peak of absorption of the water, you see that in band 4, all the data are encompassed between around 0 and 13 hundredths, more or less. You see, with a very low standard deviation. So, and the mean, you see, is 64. So around 60 in this data, I could find all the different data with a very low standard deviation. So let's check if these things is possible. So how we can do these things here? Okay, go to the data manager. All right. And in the data manager, let's, for example, from the 10 meters, let's check the first bands. I'm enlarging these windows. Okay, this is I'm sorry, near infrared bands. You see, this is the band 8. So I'm loading in the views in the left side where I have all the 10 meters data, and I load that in grayscale. All right. So let's load that in grayscale. Here it is. And you see that the water in this case, I'm enlarging, I'm zooming out, you see is very dark. And we mentioned the facts that this water is comprised, the mean value in this band is around 60, all right? With a standard deviation of plus or minus plus 11, something like that, all right? So, I mean, let's check if we can, with a color composite, I'm sorry, with a density slicing to define the water. So in this case, I'm going to this data. You see, this is this one, all right? It's in the layer manager is highlighted. Right click with the mouse and go to the new raster color slice, all right? So I'm selecting the bands. I need to enlarge everything here, otherwise it's difficult. All right, but this is the band. You see, this is the band 8. So I'm choosing this band. All right, and you see, as default is defining, you see something like uh, uh, you see here 16 different classes. But you see that also starting from here, water seems to be mostly in the violet violet value. And you see, for example, the violet is comprised between 1 and more or less 900. But we check that, I mean, the data is comprised between, let's say, 1 and 1300s. So I mean, let's remove all these lies as we did in one of the first labs. let's add a color slice, and from here, just changing the color. So for example, let's define a blue one, this one. We are comprising this interval between 1 and let's check 1300s. All right, here it is, and you see that if I'm going to go to these things here, you see that we have many different things. But starting with these things here, you see that in the case of Rome, you see here I have also the highway that is surrounding Rome, apart from the river, and there are many things that offshore, for sure, there are not water. So this interval is too big, seems to be too big. So let's check if reducing this interval, it's the situation is better. Okay, is becoming better than that. You remember we have this value around 900. Let's check if in 900 the situation is improving. You see that it seems to improve. We have still some things here that is not really clear. For example, this lake is okay, but this is not really okay because there are more water here. For example, you see this water, okay, is very nicely extracted. Maybe we can change the minimum value. Let's check if we have that in this range. No, this is not okay. You see, I mean, we can put, for example, 100, but 100 is not enough. And so let's check, let's put that like before 1 to 900. And you see that in 1 900, it seems to be okay. At least all the water is here, but you see that we have also other things that for sure is not really water, because we have this water, but not for example, I'm not really sure these things here, for example, are roads. So if we are going to select 800, for example, here, you see, I'm diminishing the interval, the water is here, but you see we have still roads inside. So the only thing is to reduce this interval, and you see that reducing this interval, I'm reducing also the facts that I'm extracting from one single band, also things that are not really water. And you see, maybe I can go back just to 500. I'm just trying to do these things because it's not really an exact opinion. It's not a quantitative analysis, but just on the feeling on what we are doing. So you see here, there are so other outliers, but seems to be something that could be defined. Let's decrease these things here. So you see that the water of the Tevere rivers is more or less well extracted here, and let's check if the other water is there, and you see that almost all the water has been extracted from here. Also these things here that is of course artificial. You see, it's an artificial basin. And let's check if the other area are extracted, and this seems to be extracted. So that could be one possibility to extract water. So when extracted the water, this is the raster slice. Okay, let's close that. Of course, we need to implement this operation from 1 to 400. So this is the 16 classes. I can remove these things and I can again, because I forgot to save, I'm going again in the same operation. I'm using band 8A. I'm deleting all the different things. I'm adding a slice using the blue, and I'm encompassing the range from 1 to 400. And this is what I defined. Okay, I forgot to click OK here before. And just clicking OK. All right, this is the results of the data. All right, so what we can do here, you see we have in the layer manager, we have the raster color slice, this image here. that is this frame here with all the image and the blue and the water defined in blue. So I can right click here and I can export this layer in TIFF. And so, I mean, I can choose where I put the data, and I can check and save this file like permanent water, uh, and then with a space density slicing in order to check and to define the facts that I extract this permanent water with a density slicing. So I'm saving this file here. So I'm opening that and I'm clicking OK. I'm not displaying the results, checking the box without because I have already the data here. So I mean, I'm saving this data, and these TIFF files will encompass, of course, also the reference system. So I will have all the information concerning these things here. So let's check if everything is there. So I'm going to wait. I'm going to the my directory. So this is Rome. And you see, I have this file here, permanent water density slicing. And this is, you see, is quite big, the image, because it's more than 300 megabytes. So pay attention, because I mean, the things are becoming tough because the file are quite big. All right, so this is the possibility to extract, for example, these things. Let's check if we have other more possibilities. For example, let's concentrate, and I mean, I'm closing these things here, and maybe I'm just, this raster color slice, I can take out that from the layer manager, so I'm removing that, and I'm also removing the single bands here. Of course, I'm removing that only from the visualization. I'm not removing from the data. So now we can go here. This is the build-up areas you see here. So for example, now we can check if we can operate with the scatter plots. So in order to operate with the scatter plots, for example, we can take into consideration, for example, let's check if the built-up areas could be a nice case to evaluate with the scatter plot. So I'm going here to the region of interest, built-up areas, right-clicking with the mouse, and I'm going to check the statistics here. All right. You see, these things here is quite flat. I mean, all the values are in, you see, these black lines is the mean value. And so, for example, you see, we can try if we have some data where some bands where the results is more or less the same. For example, you see that in band 2, 3, and 4, in this case, that means band 2 is the green, band 3 is the red, and band 4 is the near infrared. You see that the mean value is more or less 2,500, more or less, in these three bands, okay, with a standard deviation of around 1,000. So that means that all these values are roughly divided into, let's say, 1,000 to 4,000, all right, roughly speaking, all right, 1,000 to 4,000. And for example, we can check if in band 3 and 4, we can find the part of the scatter plots where this built-up area is. So uh, let's check if it's possible. So we can close the statistics concerning the ROIs. Right, so we can extract the scatter plot of band 4 and 5. How we can extract the scatter plots? You remember, we can go to the main menu in display, and you see here we have the 2D scatter plots. So clicking on the 2D scatter plots, I mean, we have these windows and we have these two bands here, for example. And in this case, we have, let's check, we have band, you see in the x-axis, we have the infrared band, you see it's 830 and 2, and this is in nanometers. This is the near infrared, and this is 664, that is the red. So I mean, we mentioned the facts that we have this data that is more or less the same for band 2 and 3, and you remember that these data are, are in this part of the histogram. Because there's a very strong linear correlation because to the same, more or less, same values in the band that is related to the near infrared, we have more or less the same value of the red. So we mentioned the effects that are around from 1000 to 4000. So I'm expecting that these data are here. So let's define a colors. Let's use the same we use, for example, for the built-up areas, this one, and I have the feeling that these data are more or less in this part of the histogram. You see, more or less. Let's check if I'm my guess is okay, and you see that it's not bad. My guessing. You see that the data are more or less in that position. But of course, you see, but when I'm zooming out, you see that the histogram is changing, of course, because what you have seen here is depending on the dimension of these windows. So you see, I'm changing that, and you see that if I'm concentrating here in the city, you see that it's not bad. It's more or less what I'm representing. You see here, this is vegetation, this is all built-up areas, and here you see that we have also these lines. You remember what these lines are roads with trees on their sides. Here we have some part of vegetation. You see here that there's a park here, and you see that maybe it's too large in these things here. So I can just use more of this point here. Okay, wait, I'm extracting also this part here, right? Maybe it's too big in this case, but you see it's not bad. For example, you see here I have the stadium, and the stadium is not extracted because the coverage of the stadium has not selected as built-up areas. In this case, this is the Olympic Stadium in Rome. If I'm not wrong, the coverage is something transparent. So it's not defined as as build-up areas. More or less, it's right. But you see that is not bad, these things here, not at all. For example, if I'm closing these things here, you see everything is becoming as before. So I can just check the most part of this area again. Let's go to the again to the scatter plots. You see here again near infrared x-axis red in this part. Okay, let's check if all this part, all the very correlated part, it's something that is related to vegetation. I'm sorry, I this is the wrong color. All right, you see that is not so much, so I can enlarge these things here, and you see that when I'm enlarging these things here, you see I'm selecting more things here. You see that more or less between 1000 to 400, I have more or less the same values, all right? So let's check, for example, if, uh, I mean, uh, uh, if extracting also this value here, because this value here, I can encompass everything. You see, that is not bad. I'm extracting also from the scatter plot these things here. All right, this is only what I can do using these things here. The a very qualitative method using the scatter plots. All right. So, but you know that we can do something better in just using the possibility that we have with the band math. Okay, doing and performing the same operation using numbers. So in a qualitative way, in a quantitative way. So just double click on band math here, and we are extracting this expression. And this expression could be, for example, let's open the bracket, and we can say that B4, let's check that. I mean, we can define that, for example, okay, 1000 should be uh, greater than B4. I am sorry, there's a mistake. So B4 greater than 1000, all right, and brackets B4 less than LT 4000, all right? So this is the interval for the red. So I'm closing that in a couple of brackets. So this is the two condition that I'm establishing for the red band, the variable B4. So I am extracting an interval of digital number comprised between 1000 and 4000. And this interval, I intersect these things here with two brackets, B8, that will be the variable for the near infrared, greater than, again, 1000, close the bracket and open the bracket, B8, LT 4000, close two brackets. I'm pressing enter. There are no mistake in the expression, so please pay attention to this expression. You can also condensate this expression, but I prefer to have this verbose description that is too much, but I mean, at least it's very clear. And I'm clicking OK here, and now I'm associating the different variable. So to before, I'm associating the variable here, band 4, the red, and for band 8, I'm associating the near infrared, all right? I'm choosing the results and will be build, I'm sorry, built up areas with a scatter plot, extracted with a scatter plot, all right? I'm opening that and I'm executing the band math, all right? This is the results. You see the nothing is appearing as usual because I mean we have the auto stretch. But if we are going here to define the right clicking on the built up area scatter plots with the new raster color slice, okay, we are selecting that. We have only two classes, of course, and the first one that is a zero value, that is not no built up area, so we can put that in black, and we can put the red, that is the one value, in maroon, all right? Just clicking OK, and you see we have something that could be very similar to the built up area here, all right? You see, that is the case of Rome. And if we are going in the outside of Rome, you see I have very much. See, for example, you see this is area, but you see that in this case I've also something that is not really built up areas, but these are, I mean, you see something that is bare soils or something like that, because I mean, using these two bands. This is very similar. I mean, is reflecting in a very similar way like the built-up area. So, I mean, I don't think that that could be used, but anyway, we use that for these things here. All right. So this is the second method. And so we can, again, like before, we can go to the layer manager and to remove this color slice and also the build up areas used with starting with the scatter plots. So I can remove that, and we are in the same position as before. So another things that we can do now is just to trying to extract the vegetation. So in order to extract the vegetation, you see I have, for example, here the yellow no, not this one. I'm sorry. I'm going to the herbaceous vegetation, for example, and I mean I put that in green, and we can check if we can extract this herbaceous vegetation using something else. So in order to use something else, we can go, for example, to the spectral indexes, because this is the third way to extract information. So let's go to the spectral indexes, all right? And when we are double clicking on spectral indexes and we are selecting the different data, all right, we can use different data sets. I mean, forget the build-up area scatter plot. This is something that is still there, but I mean, we are not interested in that. We have 10 and 20 meters. Of course, let's check these things here. If I'm using 10 meters data sets, you see 4 bands, and I'm clicking OK. I mean, this operation is embedded in the spectral indices just because we put all together the wavelengths. And using these 4 bands, we can use all these different possible spectral indexes. You see here, we have a bunch, 27 different spectral indexes using the 10 meters data sets. All right. I'm closing that. If I'm clicking again on spectral indexes and I'm using the 20 meters data sets using 9 bands, and I'm clicking here, you see what we can do? We can do operation using 43 different spectral indexes. Why that? Because in these data sets, we have more spectral bands. For example, the 2 bands that are encompassing the medium infrared. So I mean, from this point of view, we can do more, more things. But I mean, we want to use the difference vegetation index. So for using the different vegetation index, I'm clicking here, okay? We can use again only the 10 meters database. I'm sorry, data sets, because in this case, for the normalized difference vegetation index, this one, we can use only the infrared and the red. So you remember that in this case, the difference vegetation index is an index, it's a normalized index that is comprised between -1 and +1. All the vegetation that is reflecting most in the near infrared will have positive values, and in particular strong positive values. All right, and so you can find the different vegetations starting from I don't know, zero 0.3, zero 0.4 till to 1, or an index that is close to 1. So let's build this different vegetation index. So let's assign a name that is not a generic spectral index is here, but let's use, for example, NDVI at 10 meters, all right, in order to, and I put that in ROM, in my download folder in ROM, and I'm generating this spectral index, all right, for all the image using only the 10 meters dataset. All right, what I'm expecting here, that all the vegetation should be brighter than the other things. And you see, all the vegetation is very bright. You see, while all the build-up areas is very dark, but also the bare soil, you see, has a tone of gray, of gray, that is, I mean, intermediate between the vegetation and the water and built-up that are very dark. You see here, so you see that all this vegetation is very dark. So let's check if, I mean, you remember that we define here, you see in this part of the image here, I'm sorry, I lose that, I'm sorry, okay. This part here, you remember, we put this area here, I put that. This is what I call the forest, while here, you see, I have what I call the herbaceous vegetation. So you see they are both very bright, but they are not the same bright. So in order just to understand what kind of value I have in the NDVI, I can habilitate from here, you see the castle location value, just clicking here, okay? And I can go to the very bright value here that is an herbaceous vegetation. And here you see in the current representation for the NDVI, I'm checking which is the value for the NDVI. You see, I'm also checking that is a piece of the ROI. Let's check in the NDVI. In the NDVI, the data is uh, uh, like this one. While I mean, if I'm going to the to here, that is uh, forest, you see that the data is lower than that. All right. So let's check which is the possibility to extract at least all the vegetation from this NDVI. All right. So from the NDVI, right-clicking from here, let's again have the new raster color slice. All right. I'm using the difference vegetation index. This is not normalized. So I mean, this is not from 0 and 1. Let's check these things here. And you see that all the vegetation you see here seems to be greenish, all right? While all the other things is here. So greenish is ranging between, let's say, 2000 and 4000, all right? 2000 here, you see more or less, and 4000 here. All the vegetation seems to be here. And also here, you see, is part of these blues, very light areas. Okay, let's check 1000 to 4000. So let's close all the slices. Let's add a unique slide that I'm coloring green, and I'm put that from 1000 to 4000 here. All right, let's check, and you see that here uh, most part of the vegetation has been extracted. You see also here, all these things here is vegetation, all this part here, and also the roads. You see where you have, I mean, trees on the side of the streets, and you see that these things here, the herbaceous vegetation, is bigger than that. So I mean, it seems to be a way to define the other values. Because, for example, if I'm adding another slides and I'm changing these colors here in the dark green and I'm putting that in the very light green, you see that if I'm taking all the other values, you see it seems that I'm extracting the different other values. So let's move to the other part of the image. You see that here I have some other parts that are very bright that seems to be very similar to to cultivation. You see here these things here that are very bright. This is, for example, the Rome International Airport, and you see there's a way to distinguish this kind of vegetation, all right? And this is the vegetation index, all right? So I can click OK on that. This is the first things I can do, but I can also go again here in the toolbox in the spectral indexes. I'm using again the 10 meters data. I'm extracting that because I'm more confident on using the other vegetation index. This one, this normalized, because the difference vegetation index is only the ratio between B4 and B3, while the normalized is what is ranging between -1 and +1. So I'm using this normalized difference index. Okay, I'm using that. I'm saving that like in a generic way, like spectral indices. I don't change the name. All right, it's calculating everything. All right, again, it's quite similar to the other. So let's go here where I'm sorry, and just to check here, we have extracted the area here. You remember, here is the area where we extracted the data. I'm moving that. All right. This is these things here. So let's go also for this index here to right clicking to create a new raster color slice. All right. Using the normalize. So all values comprises between -1 and +1. So let's check what we have here. You see, we have here everything in green and starting from green to red. So you see, we have positive values mainly. So if we are erasing and we are clearing all the color slices, okay, and we are creating only one single value, for example, the green one, let's check if it's working from 0 to the maximum values. I mean, this is the results. Of course, I mean, it's too big because we are also encompassing all the built up area that you know is very similar to 0. So let's put, for example, here from 0.1 to zero point 0.9, and you see that I'm avoiding to extract to extract the built up area. Usually is starting from zero point 0.3, zero point 0.4. Let's use zero point 0.3, and you see that in zero point 0.3 I'm extracting more or less the most part of the vegetation. You see, for example, I can put that again like before. These things in dark green, maybe for example here encompassing that from zero point 0.3 to zero point 0.6, for example. Let's check what is happening. You see, I mean, I'm taking out all these things that are different than forest. Is not enough. Let's put 0.6, 0.7. All right. You see, I'm extracting also other things. And so, for example, if I'm adding a new slice here and I put in that in light green, you see, I mean, now, and you see also in the histogram, we are in these two things here. So you see, for example, this one is the main vegetation, and this is another peak of vegetation. So this is the peak of vegetation we are taking, that is very bright in the NDVI, that I mean, is something that is related to cultivation on the, or herbaceous vegetation, you see here, while the other one is this one. And for example, in this case, maybe I can also take a smaller interval, for example, 0.15, let's check it. All right, maybe it's too big. Yeah, it's too big for sure, because in this part we have also the build-up area. And so, for example, here from 0.2, I mean, we should have everything. So I'm not just simply trying to do that, but I'm using, you see, uh, the histogram here. So I'm considering the fact that one of these peak is a one type of vegetation, and the other one is another type of vegetation. All right, so I'm putting okay here. I'm uh, in this case, you see, I'm extracting all the values. And for example, what is quite interesting is to go in this part of the image that just close to the coastline, and you see if you are considering this part here, you see that is I mean something that is of course is not really trees, but is a sort of herbaceous vegetation. You see that, I mean, this part here is humid and maybe there are shrub. And here you see I have all these grass, for example. This herbaceous vegetation. It seems not bad. And you see also here where I have some cultivation here, you see these very uh, bright areas, you see, they are correctly assigned, you see? And this is the case, all right? Also in this part here around the lake, you see? All right, so if we are okay with these color slice, again, with the normalized difference vegetation index with the slice, I can click on the layer manager, right clicking, and again, I can export the layer to TIFF. And so what I can put here, I can put, for example, let's call that generically vegetation, extracted with NDVI, all right? I'm sorry for before, because I mean, the normalized, the vegetation, the difference vegetation index is not normalized, so it's not in the range of -1 +1, but I mean here it is the results. So I'm opening that and I'm saving that. All right. So we will have this image saved in this layer. All right. So let's wait that is saving that. And this is the third possibility. All right. Okay, it's finishing to save. All right, that's it saved. And now I can uh, get out from the layer manager all this data. Otherwise, I mean, it's very difficult to move. So I'm taking out the spectral indexes and density slicing. All right. And also this NDVI at 10 meters. All right. So back to the original situation. So now we are in the very last method for extracting information. And this is, I mean, I have the feeling that will be the more effective that because we are talking about classification. So talking about classification, we need to check a very particular things. So we are here in the 10-meter datasets. Let's open the region of interest tool. Okay, you see we have all our areas because you see we have our different region of interest. And what we need to know from now is options just in these windows and just to compute the ROI separability because we didn't do that before because I mean we are using other methods, but before to classify we need to check if all these ROIs that we have defined, so these 5 different ROIs in my example, could be separable. So if we are clicking here, you see we have all these 5 different ROIs. So, and we can click OK. And now it's calculating with this algorithm the separability. And this separability, the matrix of the possible separation, is computed from 0 to 2. If the value is very similar to 2, that means that the rows can be separated. All right? If it's close to 0, that means that the separation is not granted. I mean, the two rows are not separable at all. So let's check the results. So you see permanent water bodies, if compared with the built-up areas, the values you see is very similar to 2. With forest is 2, and also with herbaceous vegetation, and also with bare soils. So the permanent water bodies using these 4 bands is completely separable. For the built-up areas, you see that the values are very similar to 2. So also built-up areas could be separate. The forest, you see, they have a value that is not really close to 2 for the herbaceous vegetation. Of course, there are 2 kinds of vegetation. And you see that the value is 1.4 to 1.7. So that means that it's, of course, we can separate that, but not as good as, for example, forest from permanent water. For the herbaceous vegetation is the same comparing with forest. And for the bare soil, you see the values is very close to 2 for all the other classes. So that means that the bare soil could be separable from all the other classes. So you see the pair separation leads to most. You see that all the other couples are separable. The least separable class is, of course, forest and herbaceous vegetation. So we can expect from the classification method that we can confuse part of the forest with the herbaceous vegetation. Of course, we know that, but now we have numbers in order to quantify this possible separability report from here. All right, so we can close that. We can close also the windows for the region of interest, and now we can classify. I'm not classifying with all the methods, and I'm classifying only with one, not generating the rule images. But if in order to test the different results, because I mean I not have time to again to define all the operation using all the classification, you can start with an unsupervised classificator in order to see if you can extract the different areas of if there are more than these areas on the images, and then you can use all the possible classifier. For example, you can also use the maximum likelihood that you know is not very suitable for this kind of extraction of land cover classes, but the rule images, I mean the probability to belong to this particular class could be used as in the other methods, using, for example, a band math in order to separate part of the surfaces from the rule images. You remember that. But I'm not performing this operation right now because I mean, otherwise this lab will last for hours and hours. So I need to be concise. And in order to be concise, I'm going to the classification folder here in the toolbox, and I'm going to the supervised classification because I have the region of interest. And for example, I'm using only, in this case, the spectral angle mapper. All right, double clicking on spectral angle mapper, and I'm using the NDVI at 10 meters. All right, the original data, the full scene, all the bands. All right, and I'm sorry, this is not this is the NDVI, this is the things. This is, you see, 10,000 by 10,000 more or less for 4 different bands. I'm using all the spatial subset, all the spectral subset. I'm using all the 4 bands. Clicking OK here, and you remember now I need to import from these windows the ROI from the input file, and you see I have these 5 different classes. I select all items and I press OK. All right. So it's calculating all the values. You see, these are the values with all the colors. And these are the wavelengths and the facts that it did match all these classes with these different colors, all the different rows. And now it's working, it's ready for the classification. So in order to classify, I can simply click here, apply. All right. We are using not this value, maybe we can use zero point 0.2, for example, and the results, the output results, I will choose the results, and I'm taking that, I'm considering the fact that I'm naming the file some, I'm sorry, 10-meter resolution, all right? I'm opening that, I'm not outputting the rule images in this case, all right? And I'm pressing OK. All right, now is comparing the spectral signature of every single ROI out of these 5 that we defined, and is assigning every single cell to a particular ROIs. If this cell has a spectral signature that is different from these, from the spectral signature we extracted with the ROIs, that cell will be unclassified, all right? And the colors of the classification will be the same of the colors we assign to the rows. Okay, you see, that's it. I mean, remember that this end member collection of the sum is still here. So let's cancel that. And you see, this is the results of the classification, where you see we have bare soil, sparse vegetation, and everything. But you see, one thing that it's really evident from here that I mean the vegetation seems to be, and the water, of course, seems to be not bad. You see, but you see, not all the water has been classified. And you see here we have in the terminal of the airport, you see that the runoff here and all the buildings of the terminals are classified as you see build-up areas. So it seems to work with these things. But you see that if we are moving to the cities, you see I have this particular buildings here, but I have also many pieces that are not classified as build up. You see, for example, these things here that is something that should be a church is classified like a build up, but also has yellow. So that means that, these things here is not really precise. You see, more or less we have this kind of classification, but there are many things that should be buildings, but they are not. You see, in this case, for example, here and here, you see, in this case here, if I'm zooming here, this part should be build-up area, while is bare soil or sparse vegetation. Because the different things are these the two different surfaces are very similar to each other, right? Okay, so stating that this is the problem, maybe we can do another thing. And what we can do, we can just, for example, go to the data manager, and we can, bottom of the list, this is the sum, we can, right clicking with the mouse, we can close this file, all right? And of course, taking out also for the layer manager. I'm not really satisfied of that. And how I can perform again? I can go again to the spectral angle mapper. I using the 10 meters datasets, clicking OK. I'm import again, like before, the region of interest, but I'm not using all the region of interest. I'm using only the first four. I'm not using the bare soil on the sparse vegetation, because it's too similar to the built-up areas in this case. Let's try to do these things. Okay, we are using only four classes. All right, so it's calculating all the values for these four classes, and now we are applying using the same values as before. Point two, we are choosing the same file as before. We are overwriting everything. We are not using the rule images. I'm pressing OK. All right, this file is still there, but I'm not satisfied at all with the results. I'm clicking OK. So I'm reclassifying with the spectral angle mapper using only four classes in order to check if just getting out the bare soil rows, I can improve the classification of the built-up areas. Let's check if it's working. All right, now it's finishing. Okay, I can cancel these things here, and you see that the result is much better. All right, so this is all the built-up areas. You see here, I have many things that are not classified as bare soils. You see all this part here are not classified. These things here, for example, but in this case, is not. Is not confused with the built-up areas. So this classification is more confident with this classification. There are a wide range of cells that are not classified, but as I told you several times, it's better not to classify that to confuse the classification. So in this case, you see the things that is related to the fact. You see here, for example, I have all the Termini railway station is classified. Okay, this is built up areas because it's something that also related to the rails and whatever. And also here you see I have the vegetation, and also this road here that is bordered by trees is classified like vegetation. That's okay. That seems to be not bad, this classification. Of course, all this part here that you see is the place that we have, a square that we have just in front of the Stazione Termini, that is sure is something that is a mix of vegetation and other things. It's not classified, but this is better things that before, because before we misclassified the different classes. So you see, this is not bad. So the problem is now that, for example, we can use this classification for for uh, um, the classes, for example. But of course, we are missing the bare soil. So the bare soil could be extracted in another way. So for example, let's use, for example, another classificator, for example, the maximum likelihood classification, all right? In the maximum likelihood, we are using only 10 meters with all the bands, 4 bands, okay? And we are using only the bare soil vegetation, all right? And what we are doing here, the probability threshold, let's put that to 0.7, for example, and we are saving the results as uh, ML, maximum likelihood for the bare soil. All right, let's open that. And we are also saving the rule image. Only one rule image, of course, we will have. So ML rule for bare soil. All right. Let's try to classify with this classificator only over this single class. All right. So let's check which will be the results. I have the feeling that the results of the classification will be very disappointing, but maybe the measurements, the discriminating function we are using in this case, that is the probability, could be useful for the definition of this class. Okay, so you see here we have these the results. You see that I mean it's classifying something, but you see it's very limited. You see only this part and not this one, for example. But I mean, let's check the rule image. So I'm closing these things here, okay? And this is the rule image, okay? You see that the rule image is whatever is unclassified, and I mean, uh, all right, so I'm sorry, I just want to have only this one, okay? This is the rule, so whatever is bright is close to this discriminating function based on the maximum likelihood. So whatever is bright here means that is has a very high probability. You see that the water here is very dark because the probability to be of the bare soil is not probable at all. While all this area here, for example, are very bright, while also part of the city is not bright enough in order to be comprehended in these values. So also for this bare soil, so the rule image, right click on the rule image, use the raster color slice, okay, and we are using the rule, you see. Let's press OK. We will have 16 different classes. Okay, that's no problem. You see the most part of these things is comprehended in the in these values. So I mean, we are checking very high values. So let's close all these things here. Let's check a values here. For example, comprise between point, 0.7 to all the other values. Let's check if we have something. No, it's not. I'm sorry, this is my mistake. Zero point 0.7 to the maximum value that is around 18, if I'm not wrong. I'm sorry, I'm changing. The bare soil is yellow. All right. I'm sorry, there's a mistake here. All right, cancel. Let's go. I'm sorry, I'm removing these things here. I got lost. Again, I'm here from the rule image. I'm extracting the new raster color slice. I'm sorry, I got lost. So this is the distribution of the data. You see that is more or less here. It's all comprised between this value, of course. So this is minus 18. This is the maximum value. Now let me check. Yes, this is maximum. This is minus 18, but this is not really the right things. So I mean, let's delete everything. Let's associate a new interval. For example, from, let's check, minus 20 to minus 18. And you see here, for example, you see I'm trying to extract, I'm sorry, I'm, I'm, I'm just extracting things here. It's not enough. So let's check if I can do that with minus 40. And you see that it's minus 40. I'm extracting a very large part of the things, maybe too much in this case. But you see that, I mean, there's a way. And so if you are calibrating all this procedure, for example, let's check, for example, minus 30. I mean, these values, they are negative. They are not make sense in the rule image for this classificator. But I mean, it's an error of calculation in this case. But you see that most part of the bare soils are extracted with this method. So I mean, for example, if we are taking into consideration all these areas, and for example, I mean, we are checking what is what is comparing with the results of the classification. I mean, maybe this is not bad at all, the possibility to extract these things. All right. So, I mean, how we can uh, finish all these things. So, I mean, just remove these things because it was just a simple exercise. If we are using only the results of the classification, of course, the results of the classification, that is, for example, this one, I can use these things here all together. And so, for example, if I'm taking only the bare soil here, I'm sorry, this one, and I'm visualizing all these things here, you see, I can add something, you see, using these things here. You see, I'm adding something, all right? So how can I can just encompass all this data? Well, in order to encompass all this data is not really difficult because, I mean, for example, for the classification, the spectral angle mapper classification, if I'm right-clicking and I'm performing the quick starts for this layer here, you see that I have how many values I have? I have, of course, 5 different values. The 4 classes that I've used, 1, 2, 3, and 4, that are in this order. The first one is the permanent water bodies, 2 build-up area, 3 forest, and 4 herbaceous vegetation. 0 value is not classified. While here, and this is the data for this classification, if I'm taking, for example, the rule image here, I mean, I can extract only 2 classes, and I, for example, extract like before, only, for example, from this classification, I can extract only these things here, that is the yellow, you see here, because if I'm extracting the results, I mean, the quick starts from the maximum likelihood classificator, you see, I will have only 0 and 1 data. 0 is not classified, 1 is the bare soil classification. All right. So what we can do in this case, we can do a very simple thing. For example, we can perform in order to perform a union of the two different files in one single file. We can use, for example, these things here, this particular operation. So we need to add this file here, so the classification performed with the spectral angle mapper with the one performed with the maximum likelihood. The only problem is that if we are adding these two values, I mean, that is not working because you see, I mean, the problem is that with the number 1, we have here the bare soil and here we have the permanent water bodies. So, I mean, it's not working in this way. So, I mean, we need to perform another operation. So, pay attention, remember which are the validity of this data, of these two classifiers, and let's perform this operation. So let's go to the band algebra. Let's perform the band math operation. And this band math operation will be like this one. Open B1 multiplied, for example, 10, all right, plus B2, all right? So that means that to the value B1, I multiply this value B1 of the bands with B1, of the variable B1, with 4 times 10 times, all right? So if I'm selecting and if I'm associating to B1 the results of the maximum likelihood classificator, I mean the unclassified times 10 times will be 0 again. Here will be 10. So if then I'm adding all these values, the results will be this 5 number, 0, 1, 2, 3, 4, and in the ideal case, the other values that will be 10. Okay? If I have cells that has a double classification, that means that the values here, the value 10, will be overlapped with other values. And so that means that all the values that will be more than 10, so for example 11, 11 will be a cell that is classified like bare soils in this classification as a permanent water in the other. If I have the 12, will be bare soils mixed with built up areas. 13 with forest and 14 with adventures. So I'm just changing the magnitude of the values of these two things in order to check if I have also overlapping of two classification for every single cell. If I have values more than 10, that means that in particular cells, there are overlapped cells. All right? So let's press enter. Of course, the syntax and the expression syntax is okay. So I can press OK here, and I can add to B1 the maximum likelihood and to B2 the sum. All right, and let's save this file here. Final land cover map. I'm very optimistic. All right. I'm open that and I'm click OK. All right, you see it's a very simple operation. You see it's of course in only in panchromatic because I lose all the different values. But I mean, if I'm from here, I'm extracting the quick stars from here, I can simply understand if there are mixed classification. You see, I have 1, 2, 3, and 4, 5, 6, and then 10, and you see, I have not any more value that is more than 10. All right. So that means that what I classified as bare soils in the maximum likelihood has not been classified in other classes here. All right. So how can I assign the original color to these things here? Well, it's not hard at all because if I'm right clicking here, of course, I'm using the new raster color slice here. I'm using that. Okay. I have, of course, 10 classes, but now I can delete everything and I can add the first class. The first class will be black. All right. From 0 to 0. All right. Very simple. All right. Second class that will be, you see, in blue, dark blue, 1 to 1. All right. And this is the water. You see, I mean, unfortunately, the Tevere River is not blue, and this should be corrected in some way. I mean, in this case, if I don't have the blue values, that means that I need to improve the region of interest. Then I'm adding the third class, and the third class, you see, is the maroon one. So the maroon one here is 2, 2. All right, is the built up areas. You see here, built up areas. So let's go to Rome. Here we have the built up area. All right, we are adding the fourth one. The fourth one is the forest in dark gray. So here I have from 3 to 3. All right. This is the forest. All right. Then I'm adding the other one that will be in light green. This one, this is class 4. All right. Here it is. And then the last one is the class 10. That is the bare soils that will be in yellow. And so here, only what is ranging between 10 and 10. Here it is. All right. Clicking OK, and this is the results of the classification, encompassing, for example, in this case, 2 different classifications. You see here. All right. It's not bad. All right. If I want to discharge, I want to save the results of this classification. You see, I have also clouds here that are classified as bare as built-up areas, but of course it is not the case. I mean, because I'm only interested in this area. All right, so I can go here in the raster color slice of these things here. I'm export layer to TIFF, and I mean, I can use only these things here. All right, if I want to sub-select these things here, I can simply extract I can extract only one single pieces of these things here, or I can extract everything, just simply exporting this layer to TIFF. All right? And so this is the results of our final classification. Of course, this is not, I mean, precise at all, because I mean, what we can do, but I'm not, of course, re-explaining everything. What we need to do after all these things here, after the classification, is just going again to the classification folder here, and let's say here, and of course, we need to go to the post classification, because one thing that I did ask to you to perform, it's also the confusion matrix, the calculation of the confusion matrix using the ground truth ROI. So that means that, again, as a previous lab, you need to extract other ROIs that you will use for the same classes that you will use as truth ROI in order to select the results of the classification. And of course, you can use as the results of the classification also this last file here, all right? Because I need also to have all this data in order to check how good is your classification. And consider that in this case, the overall accuracy and the accuracy for every single class should be at least more than 80% for sure. Better if it's around 90% or better, all right? So I mean, check out the different ROIs and check that the matrix, the confusion matrix, it's okay, all right? So I mean, this is just a brief description on the different algorithm you can use. I mean, you can, of course, classifying everything, but things that you can do just to finish these things here, just because, I mean, I also mentioned to you the possibility to use also the 20-meter data set is this one. If I move into the 20-meter data set, this one, I want just to check if using more bands, I can be more precise on the classification, for example, of the bare soil. All right. So I mean, in this case, what we can do just for the last example, I can go to the spectral angle mapper here. I'm using the 20 meter and using all the bands, all right? So I'm importing my ROIs, and you see I have all the ROIs. I'm using all the 5 ROIs in order to check if using more bands, I will be more precise in extracting the best soils and not confusing that with the built-up areas as using only the 4 bands. Clicking OK, and you see we have all the data here, and now I'm applying using the same parameter as before, 0.2. I'm not calculating the output rule image. I'm choosing the output name like as SAM to 20 meter. All right, let's check if something is changing. And I'm classifying I'm classifying the image using these things here. All right, this is the results I got as the last things here. I mean, adding the two partial results of the classification. Let's check in these views. Is the result on 20 meters is better than that one? Okay, this is the results, and you see that the results is more or less like before. I mean, that means that you see, Berso is also using other bands, is confused with the built-up areas. You see, so I mean, it's not a problem of bands. Of course, that is a problem of the definition of the region of interest. In my case, I mean, the region of interest are not accurate at all because you see that are separable, the two classes. But unfortunately, here I cannot separate that with the classificator. So I mean, the way that you have to check in the final assignment is if using other algorithm of classification or other methods like the ones I explained to you and I show you in this lab, you will success in order to extract all the classes I asked to you. All right. So I think that for this last lab, it's enough. So thank you very much for your attention. And as usual, never give up. Bye-bye.